All right, so yesterday we talked about how to do some operations with matrices, like adding them, subtracting, doing scalar multiplication. That was just when you took a number times an entire matrix. Now we're going to talk about how to multiply matrices. So this works a little bit differently. We can't just multiply the elements inside of a matrix and make them be equal. It doesn't quite work that way. So we need to talk about what has to happen on your matrix, like what you have to check for before you can even do your process. So the rules say that when you're looking at two matrices, they have to have the same number of columns in the first matrix as rows in the second matrix. When you're going to start multiplying, there's a little bit of a process we have to follow. We're going to take all of the numbers in the first row times all of the numbers in the first column on the second matrix. So you're going to take something from the first matrix and multiply it times something in the second matrix. Then what you're going to do after you do your multiplication is add up those products of all those elements. The resulting matrix that you're going to end with will come from the dimensions, but it'll be the number of rows in your first matrix and the number of columns in your second matrix. So right underneath this, they're just showing you an example of how this would work in like general forms. Like we're not necessarily working with numbers quite yet. But if you had two matrices like the one shown here, you first have to check their dimensions. So this first one is a 2 by 3 matrix, and the second one is a 3 by 2. First thing you need to check is that these numbers here and here match. Okay, if these numbers don't match, then you can't multiply the matrices. Since they're both 3s, that means that everything will have something to pair up with. So we should be able to multiply them. Now the new dimensions of your new matrix, those come from the outside numbers. So the 2 here and the 2 here. Those are going to tell you what your new answer would look like. So even though I started out with a 2 by 3 and a 3 by 2 matrix, I'm going to end with a 2 by 2 matrix when I'm all set and done. Now what they're showing you over here, it looks like a lot of letters and numbers because it is, but we're not actually going to see problems that look like this. They're just showing you if these were your elements from your first matrix and these were your elements from your second matrix, using some of that notation we've talked about the last couple of days. This is the pairing of pieces. What they're really doing is they're taking this first row, all of those numbers, times this first column. That's what they wrote here. So you multiply all the individual pieces together and then you add the numbers together after you've multiplied them. Then once you do the first column, you move on to the second column. So you multiply to this one, and that would give you this next set. And then once you get all those columns done, then you move on to the next row, and then you multiply by those columns. Okay, so on this last one, this would be, when we're finishing it off, we'd be taking this row times this column. And so I'm just going to fill in what that would look like. And then we'll get into examples with actual numbers. But so this one, you would be taking that first term, which says M21, and you would take that times the N12. Then you would add that. The next one would be the M22, and then N22. And then you would add that to the last two terms, which is the M23. And I'm running out of room, but this would have N32 after it. When you're working with an actual matrix, though, you're actually going to be multiplying numbers. So this is just giving it to you so that it could be any matrix that you would want to apply it to. First thing you should always check, though, are those dimensions. If your dimensions don't match on the interior, then you're not able to multiply the matrices. So if that happens, then we just can't do anything with it. So a couple of examples here. If I have matrix A, which is a 3 by 4, and matrix B, which is a 4 by 6, I'm just checking that this 4 and this 4 are the same, which they are. So that tells you that you are able to multiply, and your new dimensions would come from those first outer numbers, the 3 and the 6. So when I multiply matrix A and B together, my new dimensions would be 3 times 6, or 3 by 6. The second example I have here is not possible to do because these numbers on the interior here do not match. So if they don't match, you're not able to do that. So look at the practice right underneath it. Are you able to multiply these two matrices together? Yeah, because you have a 3 here and you have a 3 here. What would be the dimensions of your new matrix?
Would it be 4 by 5?
Yes. So whatever CD multiplied would become a 4 by 5 matrix. Okay, so now I'm going to actually show you how we would multiply. So if I look at this next example down here, first thing I'm checking is, can I do this? So this is a 3 here. Oh, doesn't want me to highlight. This is a 3 here. This is a 3 here. So I can multiply. The outer numbers, though, this 2 and this 2, tell me what my new dimensions would be. So that's why I know my final answer here is going to be a 2 by 2 matrix. 2 rows, 2 columns. So I'm going to start my process. We're going to take this first row times my first column. Okay, so it's going to look like this. 4 times negative 2. Plus negative 2 times 5. Plus negative 7 times 3. You guys follow the order I'm putting those in there?
Mm-hmm.
Once you've got your first row times your first column, you now go on to your second column. Still the same row. So I'm still using the 4, negative 2, negative 7 for my first matrix, but now I'm going to take it times 1, 0, and 2. So that's going to say 4 times 1 plus negative 2 times 0 plus negative 7 times 2. Once I've got that last column done, now I move on to my second row. So now I'm dealing with this row, and I'm going to take it times this column first. So everything's going to look similar except for those first numbers in my pairings are going to change now to my second row of numbers. So we've got 6 times negative 2 plus 3 times 5 plus 5 times 3. Okay, and then what's my last pairing going to be?
Bottom row, the first one times the second column.
Yep. There you go. So that's going to look like this. 6 times 1 plus 3 times 0 plus 5 times 2. Okay, so that's all the matching up of elements, okay? Once you guys get really comfortable with this, you don't need to write all of that out. A lot of that is just going to be calculator work where you're just typing in your equations. But now when you get to this point, it's just to do multiplication and addition. So if we look at the first set of numbers here, 4 times a negative 2 would be negative 8. Negative 2 times 5 would be negative 10. And then negative 7 times 3 would be negative 21. So what's negative 8 plus negative 10 plus negative 21? Yeah, so negative 39 is going to be your first element in your final matrix. Then we're going to keep going. So this next numbers would be 4 plus 0 plus negative 14. So what does that come out to be? Negative 10. Okay, the bottom here would be negative 12 plus 15 plus 15. What does that become? Careful. It's negative 12 plus 30, so 18. And then this last one, 6 plus 0 plus 10?
16.
16. There's your final answer. Okay, so it's a little more of a process. It's not as cut and dry as they were yesterday where you just this term and this term, you add or subtract them. We have to go through a little bit more motions when we're doing multiplication. But the math really that's going on here is not super complicated. You're multiplying and you're adding. All right. Yeah. Go ahead and I'll give you a minute or two to try to do these two on the bottom here. Okay, I've got that first one kind of all written out, but like I said, some of you will get to the point you don't need to write all that out. You can just start to actually multiply and add. What do you get for final numbers here? This should be 10 plus 3. 6 plus 6.
12.
Negative 2 plus 12. This one would be 20 plus 1. 12 plus 2. And negative 4 plus 4?
0.
0. Could you multiply the second example? Is it possible to do? What are the dimensions of the first matrix here?
You can't.
Why not?
It's 1 by 3 and 1 by 2.
Yeah, this is a 1 by 3, and this is a 1 by 2. So we can't because the 3 here and the 1, those inner two pieces from the dimensions don't match. So this is not possible. If you tried to multiply, you'd get stuck because something would not have a piece to pair up with. All right, so now let's take this process here. Let's apply it to a couple of problems on this next page here. So they're giving us a chart that's describing some prices at different scenarios. Like this first one is talking about bookstores, one that's on campus and one of them that's off campus. And they're giving us the cost of the different things that we're looking at purchasing. So it says that we need to buy 5 books, 7 notebooks, and 3 binders from this store. But they want to know which one should we go to? Like which store, should we spend our money on campus or spend it off campus? So where they got these numbers from, like this first set, the 573, that comes from the quantities of things that you want to buy. So you want 5 books, 7 notebooks, and 3 binders. Okay, so the 5, 7, and 3 comes from there. The rest of these numbers here, those are all coming up from up here, the table that they gave me. So the costs at the 2 different stores. I want to figure out like which place is going to be cheaper. So I'm going to do multiplication here in order to figure out how much it would cost me to buy all of these things at the store. So like we did on the previous page, we're going to take on this first one, this row times this column. So you're taking 5 times the 110, 7 times the $1.50, 3 times the $2.50, and then you're adding those all up. I want you guys to do that. You're going to do the same thing for the second store. You're still keeping those same quantities, but now we're going to take 5 times 100. 7 times 1.75. And 3 times 2.25. So you're going to multiply all of those, add them up. This should give us our total cost for the store. So I want to know how much it's going to cost me per store here. So if you have a calculator, start working on that and tell me what you get.
For the first one, I got 568.
Good. 568 for the first store.
And then 519.
Good. 519 for the second store. So which store is cheaper, the on campus or the off campus? off, right? Because this first column of numbers was using all the prices from the on-campus bookstore. So it would be better to shop at the off-campus. And then they are also asking, how much money will you save? So what's the difference between those two prices?
$49.
Good, $49. So I would say $49 if I shop at the off-campus store. So it's still multiplying matrices. It's just giving maybe a little bit more context here, being able to apply. So instead of looking at a big chart like this with all these different cost values, we could rewrite it as a matrix and still figure out how much it would cost me for those things. Okay, so we've got a practice problem down here. It says you are going grocery shopping. You need 2 gallons of milk, 3 pounds of hamburger, and 1 package of buns. Where would you shop? So they're giving you store A and store B prices. Let's just set this up. So if you grab the quantities of things that you need from up above, you need 2 gallons of milk, 3 pounds of hamburger, and 1 thing of hamburger buns. And then store A is $2.79, $3.65, and $1.70. And store B is $2.55, $3.80, and $1.65. So why don't you guys go ahead and take a minute there and figure out how much it costs to shop at each store, and we'll see which one's cheaper. Once you have prices for the stores, go ahead and let me know what you found. Anyone have dollar amounts?
1823, 1815.
Good, so which store is cheaper?
BB.
Good, B. So store B is where we would probably be better off to shop at. Okay, questions on matrix multiplication like that? All right, if you guys go to the last couple pages here, these last few are talking about how we can look at a shape that's on a coordinate plane and use matrices to help us perform transformations. Remember, transformations is just when we're moving shapes around or we're dilating or shrinking the shape. So we're making it bigger or we're making it smaller. When we're doing this, how we're going to write out our matrices is whatever shape you're working with, you need to know what the coordinates would be for that shape. So over here I have this triangle. We're going to use this same triangle for all of our problems here at the rest of the section. So this point is at 0, 0. This point is at 4, 2. And this point is at 3, 5. Okay, but how they wrote that over here in the matrix is they put all the x coordinates across the top, so that's my first row, and all of my y coordinates are on my second row. Now they kept them stacked, so like the 0, 0, they're stacked on top of each other. The 3, 5, they're stacked on top of each other, and the 4 too. So when you're writing out, you don't want to just like throw in the numbers wherever you want. You want to still make sure that your coordinates are right on top of each other inside of your matrix. But the whole top row is your x coordinates, the whole bottom row is your y coordinates. Now they might start to ask you to do things like move it this way, put it in this spot on the graph, and we just need to know how do we reflect that when we're doing matrix operations. So the first example they say is to move the triangle 3 units left and 1 unit down. Those are 2 different movements that are happening. Left means it's going to impact your x-axis. Down means it's going to impact your y-axis. You've done transformations like this before, but like with quadratics and stuff like that. If you're going left, that's a negative movement. So what they did is they took this matrix from up above, the original one with all the coordinates, they just dropped that down here. But then because I'm going 3 left, that's a negative amount. So they wrote -3 for all those x values. 1 unit down is your y coordinate, but that's also still negative because you're going down. So they wrote -1 underneath there for the y's. All you're doing then is adding these matrices together. So they took 0 plus -3, 3 plus -3, 4 plus -3, and that's how they got this -3, 0, 1. If I do that with my y coordinates, if I take the 0, the 5, and the 2, and I add a -1 to it, what are my new coordinates? What's 0 plus -1? -1. 5 plus -1. 4 and 2 plus -1? 1. You could also think about, since they're both negative, that you're just subtracting from your x and your y's. But then that's my new shape. They may then want you to graph it. So back up here, I would go to -3, -1, 0, 4, and then 1, 1. And you can see how that shape did move left and down. And it looks like it went left 3 and down 1. So it's just another way to approach doing these transformations. Now that would be like a movement, like going left or right, those kinds of things. They may also want you to perform like a dilation. So this next one wants us to enlarge the triangle to twice its original perimeter. That just means they want you to dilate the shape by a factor of 2. So notice how I'm still having this original matrix here. That's all from my original triangle. I'm dilating it by a scale factor of 2. So I put a 2 out on the front. Remember what we did yesterday with this, with the scalar, is we just take that 2 times everything inside the matrix. So what would be my new matrix if I multiply all those numbers by a 2?
0, 6, 8, 0, 7, 4.
Good. And then you would just graph those. So you can see that's a dilation. It did get bigger. All right, we've got just a couple left here. I'm just going to write out matrix A here at the top because they are still going to want me to use this original one. So matrix A was from that previous page. Your coordinates were 0, 0, 3, 5, 4, 2. These last ones are wanting us to multiply by another matrix. So they're giving me a new matrix here as well, like matrix B, and they're wanting me to take matrix B times A. So we're taking this 1, 0, 0, -1, and we're taking it times matrix A. So this is what we were doing at the beginning of today. So you're taking the row times the columns. When you do this one, you get 0, 3, 4, and then 0, -5, -2. Okay, I'm still using the same process for multiplying that I went over a little bit ago. I'm just skipping over all of that stuff. But when I go to graph this, I want you to look and see what happens here. So 0, 0 is still where it is, But now 3 is going down to -5, and 4 is going down 2. What looks like happened here? How would you describe the movement that occurred on that graph? Yeah, it's a reflection. What does it look like they reflected over? The x-axis. So when a matrix is written like this, 1, 0, 0, -1, that's going to be a reflection over your x-axis here. So then the last one on this page, the matrix is just a little, like they're changing it. It's not 1, 0, 0, -1. Now it's -1, 0, 0, 1. So the signs are changing a little bit, but we're taking this matrix C, again, times my original matrix A. Oh, I'm going to finish this here. But this would be 0, 0, -3, 5, -4, 2. And then I'm going to graph this. This one is going to do a reflection over the y-axis because of they changed those signs of my numbers.
That was confusing. How to multiply. I think that is way too